So here then in question 3, we're told a pure gas X has a density of 1.86 grams per litre at a temperature of 112 degrees Celsius and 1.12 atmospheric pressure. You use these data to find MR, the molar mass then of X. Well, to start off with, I'm going to write down my values. I have a density denoted by rho equaling to 1.86 grams per litre. We have a temperature equaling to 112 degrees Celsius. 112 degrees Celsius in Kelvin is the same as 385 Kelvin. And then we're also told we have a pressure, little p, equaling to 1.12 atmospheric pressure. Or 1.12 atmospheric pressure, or atmospheres, is equal to 1.12 times 1 atmosphere. And 1 atmosphere is equal to approximately 101.3 kilopascals. So we can say then the pressure in kilopascals is 1.12 times 101.3, and then that's equal to, well, we can leave that as it is for now anyway. And we have to find the molar mass. So resorting immediately to our ideal gas equation, as we're dealing with a gas and we've got a few values, we've got a temperature and a pressure which suggests that we should be using this equation. The ideal gas equation then is pressure times volume is equal to the number of moles times the universal gas constant times temperature. Well, if we're wanting to find the molar mass, well, we know an equation that links the number of moles and molar mass. That's that the number of moles is equal to the mass divided by the molar mass. So we can substitute that in, so therefore PV is equal to mRT over mR, but we don't know the mass of the substance, of the gas, but we do know an equation that links density and mass. That's that density is equal to mass over volume, and therefore then the mass is equal to the density times the volume, which we can substitute that in. So therefore PV is equal to rho v RT over mR, and we're wanting to find the molar mass, rearranging to make mR the subject. We would then get that we can times both sides by mR, divide by PV, so we would get rho v RT over PV, and quite simply we can substitute in our, well, 1 minute, we can see that volume V cancels on top and bottom, so we can sort of put a line through that just to show that they cancel. And finally we can plug in our values. So we have a density of 1.86 times by the universal gas constant, 8.31, times temperature in Kelvin, 385, and that divided by the pressure. We've left it as this value up here, 1.12 times 101.3. And if you were to do that on a calculator, you'd get a value of 52.5. Units of molar mass, grams per mole.